everyone, I'm Dr. Rizwana, working as Professor of Physics in Institute of Aeronautical Engineering. So today we are going to discuss some definitions, very important definitions and terms related to light optics. So we know what is optics. Optics is branch of science that deals with different phenomena related to light propagation. And when we talk about different phenomena, we talk about interference, diffraction as well as polarization. And of course here we are going to discuss only about two important phenomena that are interference and diffraction. So I hope by discussing all these definitions, we are going to have in-depth understanding of these two phenomena. Then moving to those definitions, coming to first definition, define wavefront. So we know that suppose if I take a point source, right, and if I consider different particles, and when these particles are vibrating in the same phase, if I take locus of all those different particles vibrating in the same phase, then this particular locus is nothing but a wavefront. And of course, all those particular particles, they should vibrating with the same phase, of course, as I told you, and their locus is nothing but wavefront. And depending upon what type of source we are taking, we are going to get different shapes of wavefront. Now, when we talk about spherical wavefront, what I have done here, in order to get spherical wavefront, we'll take a point source, and if we consider all those particles vibrating in the same phase, what do you mean by vibrating in the same phase? First of all, you should have isotropic medium, and of course, what type of source we have to use? Point source. And if you consider light waves, which are traveling with same velocity in all directions, then the locus it is going to give spherical wavefront. Then what about the cylindrical wavefront? So for cylindrical wavefront, we have to take extended source. What do you mean by extended source? It can be a tube light, okay, or we can make use of sodium vapor lamp. So if I take extended source, and here also if I consider all those particles vibrating in the same phase, so same phase means which are traveling with same velocity in all directions in isotropic medium, their locus, it comes out to be a cylindrical wavefront. Then what do we mean by plane wavefront? If we keep our point source or extended source, it is also called as linear source at infinite distance, then a portion of spherical or cylindrical wavefront limited in a small region, okay, that is nothing but a plane, and that wavefront it is called as plane wavefront. So for that, what we have to do, it can be a point source, it can be a linear source, and we have to kept it at infinite distance. Then what you will observe here is very small portion of spherical or cylindrical wavefront. So here, how we'll represent this plane wavefront? It is represented like this. And what is the direction of propagation of light? It will be perpendicular to this plane, and such wavefront it is called as plane wavefront. Then define principle of superposition of waves. So what is principle of superposition of waves? Suppose if we have overlapping of two or more waves, okay, then resultant displacement because of overlapping or superimposition of two or more waves, it will be algebraic sum of displacements of particle due to individual waves in the absence of others. Then such particular resultant displacement it is given by principle of superposition of waves. Suppose if I take two waves, okay, and one wave displacement if I represent it as y1, and another wave displacement if it is represented by y2, then according to principle of superposition of waves, what is the resultant displacement in the region of superposition? It is the algebraic sum of displacements due to individual waves. Then define interference of light. When principle of superposition talks about displacement, interference, it talks about intensity or amplitude. So according to principle of superposition, when two or more light waves superimpose, then resultant amplitude or intensity in the region of superposition, it will be different than the amplitude or intensity due to individual waves. This modification in the distribution of intensity, it is called as interference. Then define Huygens principle of propagation of wavefront. So according to Huygens principle, if we consider each and every point on the wavefront, suppose I have one wavefront here, and if I consider each and every point of this wavefront, then what we'll observe here is from this each and every point you will have secondary waves coming out. So each point it will give rise to secondary disturbance. Those waves they are called as secondary waves, and all these secondary waves, envelope of all these secondary waves, they will give rise to one more wavefront. That wavefront it is called as secondary wavefront. Then how is phase difference related to path difference? So if you consider here it is 2 pi by lambda. So if you consider phase difference is 2 pi by lambda times the path difference. So this is the relation between phase difference and path difference. Then define fringe width. So what is fringe width? We know that because of interference on the screen, we are going to get alternate bright and dark fringes. Suppose this is our screen, and on the screen we are able to get alternate bright and dark fringes. So distance between two consecutive bright fringes or distance between two consecutive dark fringes is nothing but fringe width. So it will be in case of interference, all bright and dark fringes they are of same width, and that width of two consecutive bright fringes or dark fringes is nothing but fringe width. And then of course that fringe width it is represented by beta. Then next, define coherent sources. So what are coherent sources? Suppose if you consider two waves, I have two waves like this. Now in this case, because crust is falling on crust, trough is falling on trough, we'll say that they have phase difference of 0 degrees. And similarly, if you consider two waves which are maintaining constant phase difference, so here they are maintaining constant phase difference between them. So if we have two waves either maintaining 0 or constant phase difference between them, then such two waves they are said to be coherent sources. Then what is a plano-convex lens? So plano-convex lens, it has positive focal length elements that have only one spherical surface and one flat surface. Then define convex lens. Convex lens, it is also called as converging lens. A converging lens is a lens that converges rays of light that are traveling parallel to its principal axis, and it is relatively thick across the middle and thin at the upper and lower edges. Define radius of curvature of the lens. So here in this case, of course, so what is radius of curvature? It's the radius of halo sphere of glass of which the lens is a part. Now define focal length. What is focal length of a lens? Distance between the principal focus of a lens or mirror and its optical center is called as focal length of a lens. Then define Newton's rings. So what are Newton's rings? Here in this case, interference of light reflected from top and bottom surface of air film. And what is the shape of the air film? Circular symmetry. So what we'll do, we'll take plano-convex lens and we'll keep it on a plain glass plate. Here we have formation of circular air film, and if we consider light waves reflected from top and bottom surface of the film because of interference, we are going to get Newton's rings. And what are the shape of these rings? Circular rings. These are concentric circular bright and dark rings. Now give one example of Newton's rings. Of course, it is observed in the colorful fluorescence on water surface with a thin layer of kerosene. Suppose if you take water, on that water if you have very thin layer of kerosene, then you will observe formation of colorful fluorescence. So circular rings, that is one good example of Newton's rings. Now why is the center of Newton's rings dark? Now if you consider this setup, here at the center, lens and this bottom surface. So here we have convex lens and here we have plain glass plate. Now this lens, curved surface of lens and top surface of plain glass plate, they are going to meet at one particular point, and at this point thickness of the film is 0. And when we are going to substitute, suppose what is the path difference between light waves reflected from top and bottom surface of air film when we are considering Newton's rings? Path difference, it is given as 2t. 2t is equal to, of course, actually what is there here, if you take thin films, it is 2 mu t plus cos r is equal to lambda by 2. This is the formula. And of course here, because we are going for normal incidence, this will become cos 0. So here when we are going to substitute angle of incidence, so ultimately our path difference, it comes out to be 2t is equal to lambda by 2. So thickness of the air film is 0. So when we are talking about path difference, delta is equal to 2t plus lambda by 2. Thickness of air film is 0 at the center of the contact. So path difference, it is coming out to be lambda by 2, which is the condition for dark spot. So that's why central spot is dark. The next, explain Young's double slit experiment. So what is Young's double slit experiment? Here, of course, light have both the wave characteristic as well as particle characteristic. And here, in this case, actually in Young's double slit experiment, what we are going to do, so in this case, we are going to take single source, and light from that single source, it is made to pass through two different slits. Now these two different slits, they act as virtual coherent source, and whatever wavefronts they are getting divided at these two slits, they will be coherent. Why? Because they are coming from the single source, and because of superposition of these two spherical wavefronts, we are going to get interference fringes, that is points of maximum intensity as well as minimum intensity on the screen, and this formation of interference fringes will explain this Young's double slit experiment. Then define constructive interference. What is constructive interference? When waves which are superimposing are in phase with each other, or crust of one wave falls on crust, trough of one wave falls on trough, then intensity will be sum of their intensity or sum of their amplitudes, giving rise to bright fringe, and this phenomenon is called as constructive interference. Whereas when you take destructive interference, in this case, waves are out of phase with each other, crust of one wave falls on trough of another wave. So here amplitude, resultant amplitude will be difference of amplitude due to individual waves, or difference like resultant intensity is difference of intensities due to individual waves. And here when we talk about this wave superimposing which are out of phase with each other, we are going to get zero intensity, which will give rise to dark fringe. The next, define diffraction. What is diffraction? We know that suppose if you are keeping any obstacle in the path of light, then what you will observe here is light will bend around the corners of the obstacle, and because of bending of light, you will have spreading of light with different intensities at different points on the screen, and this spreading of light is nothing but diffraction. And on what factors does the amount of bending happens in light? Here amount of bending, it depends upon two factors. One is size of the obstacle, another one is of course wavelength of the wave. Then how did Fresnel give the reason for diffraction phenomena to occur? So what is according to Fresnel? He told that when we take each and every point on primary wavefront, we'll have different secondary waves coming out, and as we know that diffraction is nothing but bending of light and also spreading of light waves, and that spreading of light waves is nothing but spreading of secondary wavelengths. So according to Fresnel, due to mutual interference of secondary waves which are originating from various points of primary wavefront which are not blocked by the obstacle, will give rise to diffraction phenomena. And explain Fresnel's diffraction. We know that based on where we are keeping our source and screen from obstacle, we have two types of diffraction. One is Fresnel diffraction, another one is Fraunhofer diffraction. In Fresnel diffraction, our source and screen, they are kept at finite distance from the obstacle, and because source and screen, they are at finite distance, we will not make use of any lens in order to converge rays. And what is the wavefront we are using in Fresnel's diffraction? It can be a spherical wavefront or cylindrical wavefront. Then what about Fraunhofer diffraction? Completely opposite to Fresnel diffraction, we have Fraunhofer diffraction where we are keeping our source and screen at infinite distance from the obstacle, and because we are keeping both our source and screen at infinite distance, we need lens in order to converge diffracted rays onto the screen. And because our source is at infinite distance, what type of wavefront we are using? We are making use of plane wavefront. Now state the major difference in phenomena of interference and diffraction. What is the interference? We know that interference, it is because of superposition of two separate wavefronts, and from where we are getting these two separate wavefronts, they are coming from the single source. What we have done, we have used single source and we have divided light into two parts, and this process it is called as division of wavefront. And because of superposition of these two wavefronts coming from the same source or these two coherent wavefronts, we are going to get interference. But what is diffraction? Diffraction, it is because of interference of secondary waves which are originating from different points of the same wavefront. Here we are taking two separate wavefronts, and in this case we are taking the same wavefront, and here interference of secondary waves which are coming from each and every point of same wavefront are getting superimposed. But here superposition of two different wavefronts, but of course they are coming from the same source. What is a grating? So for grating, what we'll do, we'll take a plain glass, which is a transparent material, using a diamond point. What we are going to draw, we are going to draw rulings or vertical lines which are equidistant from each other. Then here, what you will observe here is wherever we have ruling, it will be opaque to light, whereas distance between two adjacent rulings, it will be transparent to light, and it will act as a slit. So what is a grating? Grating, where we have large number of slits, and all these slits are of same width and they are separated by equal opaque spaces. Then what is a plane transmission grating? This particular construction where we take plain glass using diamond point, we draw rulings or vertical lines equidistant from each other. That particular setup is nothing but plane transmission grating. Then what is plane reflection grating? Here what we'll do, now we are going to draw lines on silver surface. Here in case of plane transmission grating, we have drawn lines on plain glass, but here in this case in plane reflection grating, we are drawing lines on silver surface, and light is reflected from the space in between the lines, and that particular setup it is called as plane reflection grating. What is power difference? Power difference, suppose I have two sources, and this is my screen. I have selected one point on the screen. I have one wave starting from one source and reaching point P on the screen. I have another wave which is starting from another source and reaching the same point. Then what you will observe here is difference in distance traveled by these two waves to reach one single point on the screen is nothing but power difference. And what is phase difference? Phase, when we are talking about phase difference, it is measured with respect to angle or time. So whereas power difference, it is measured in terms of distance traveled, whereas phase difference, it is measured in terms of angle or time interval. Then define angle of incidence. Obviously, we know that what is angle of incidence. If we take a surface, angle of incidence, it is taken as the angle between a ray incident on a surface and the line, that is nothing but perpendicular. Line perpendicular is nothing but normal to the surface, that is nothing but angle of incidence. And what is angle of reflection? Angle taken between the reflected ray and the normal to the reflecting surface. And what is focal point? We know that the point where all light rays will merge from a mirror or lens is nothing but focal point. And when we call two waves to be in phase, when their positions exactly match, when crest of one wave is falling exactly on crest of another wave and trough of one wave is exactly falling on trough of another wave, then we call them to be in phase. And when we'll say they are out of phase, when crest of one wave falls on trough of another wave, so they have 180 degrees phase. Such waves, they are said to be out of phase. Then define lens. So a curved transparent object usually made of glass or clear plastic is known as lens. And what is a light? Of course, light is everywhere in universe, and usually the wavelength of visible light, it is it will range from less than 4000 angstroms and more than 7000 angstroms. So light, it is one form of energy. Define wavelength. What is wavelength? The physical distance that light travels in one wave cycle is nothing but wavelength. And all electromagnetic energy is transmitted in waves. So define monochromatic light. So in case of monochromatic light, it will have single wavelength, and here spectral line width will be very, very small, where optical spectrum contains only a single optical frequency. So these are the different definitions related to phenomena of light, that are interference and diffraction. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.